M, and as I was saying, this could be a complex manifold. Or you might prefer a variety. Or you might prefer a scheme or a stack. But actually what I'll be dealing with today is the singular analog of complex manifolds, which are complex spaces. But if you're not happy with complex spaces, you won't lose anything by assuming everything is smooth. Okay, so we want a space M such that, first of all, so it should be a parameter space for polarized varieties. So the points of the space M should be in bijection with polarized varieties. So every point gives you a polarized variety, and every polarized variety is a point in this space. And what you need is that actually further, this is something that works well in families. So if you have a family of polarized varieties, then actually you get a morphism to the moduli space that's compatible with this bijection. So a family of polarized varieties should give you a map from the base of the family to the moduli space. So it induces a map to M compatible with the first point. So to draw some kind of diagram, suppose I have some family over some base. So I have a family of polarized varieties. Each fiber of the map pi is a polarized variety. And S could be, say, again, manifold variety, whatever you like. And what really you want is that then this induces a map P to M, where the fibers over S are then mapped naturally to the corresponding points in the moduli space. So this is what I'll mean by a moduli space. To give you some examples of where you might have seen these before in algebraic geometry or complex geometry, I would say they already appeared in the first ever paper on anything to do with complex geometry, which is Riemann's thesis. So if the dimension of X is 1, so you're dealing with Riemann surfaces, and say the genus is at least 2, then you get the moduli space Mg of curves, smooth curves, X, and I choose the line bundle on the varieties to be the canonical class. So this is, as we saw earlier, the top exterior power of the cotangent bundle, which for a curve is, there's no exterior power at all, it's just the cotangent bundle. The first kind of natural higher dimensional version of this story, okay, so sorry, this was, say, Riemann, and maybe more rigorously, Mumford. Okay, so if the dimension of X is n is strictly greater than 1, but L is still equal to Kx, then you get the moduli space of what people call canonical models or canonically polarized varieties, which also appeared earlier today. This also has a very long history. So Gieseker is the first name I would associate, who dealt with the case of surfaces. Then I believe Schumacher constructed the moduli space as a complex space. And then finally, Vivek showed that actually you get a quasi-projective scheme as your moduli space, so slightly stronger than a complex space. And the study of this moduli space goes under the name of this Kähler, Shepard, Baron, Alexeyev program, particularly in relation to the natural modular compactification of the moduli space. The last example that I'll mention is that of Calabi-Yau manifolds, which are one of the other big important classes of varieties. So if Kx is numerically trivial, or say the first term class is 0 as a class, say L arbitrary, so then you get the moduli space of polarized Calabi-Yau manifolds. Okay, and this again has a very long history. I think the right names are Fujiki and Schumacher. And again, Vivek. I hope I'm getting that right. Okay. So one nice feature of these moduli spaces is that the spaces themselves are pretty well behaved. In particular, they're actually Hausdorff spaces. Usually you kind of just want Hausdorffness in any space, because it's a good property to have. So typically, one wants a Hausdorff moduli space. And actually, this is true for all of those examples. And Hausdorffness has a very concrete interpretation for moduli spaces in terms of families over the punctured disk. So if you want to actually check Hausdorffness or compactness or any kind of property of a moduli space, usually what you do is study families and then properties of families. So you translate topological properties or other properties of the moduli space into properties of families of the objects under consideration. So in our case, families of polarized varieties. So if you take XL star over delta star, so the punctured disk, to be a family over the punctured disk, then compactness slightly roughly corresponds to the fact that you could complete this to a family over the whole punctured disk. So there exists a completion to curly X, curly L over the whole disk. And Hausdorffness, this is saying that any completion is actually unique. So there exists at most one completion. And you can check that this Hausdorffness automatically follows in these examples in the center. I'll use the buttons next time. Okay. So the problem in general and why moduli theory is quite difficult is that this Hausdorffness doesn't automatically follow. So the major issue is that there are examples of non-Hausdorffness of moduli spaces of polarized varieties. So there is a Fano threefold, which is to say that minus kx is ample, say x, and a family not just over the punctured disk, but say over all of C. I'll always write this as XL over C, where the general fibers are all isomorphic and isomorphic to this Fano threefold X. But you actually get a different Fano threefold as the central fibers, so the moduli space cannot be Hausdorff. So this is isomorphic to y minus ky, some other Fano threefold. What this is telling you then, if you use this correspondence, it's saying that moduli spaces of polarized varieties aren't always Hausdorff. And if you believe me that you like Hausdorff spaces, then what you would like to do is change the problem slightly, restrict your class of polarized varieties, and then try and get a moduli space that's actually Hausdorff. So I'm going to modify my goal that I wrote way up there to the following refined goal. So the refined goal is to form a Hausdorff moduli space of some well-behaved class of polarized varieties. So form a Hausdorff moduli space of a class of, you shouldn't take this too seriously, but well-behaved varieties. And somehow the main issue in the problem is to actually give a precise definition of what you mean by well-behaved. Okay, so today, just to spoil the answer a little bit, before giving you a more precise statement, what I'll say is that we can do this now using ideas from Kähler geometry. Kähler geometry, and in particular, these constant scalar curvature metrics that came up earlier. Okay. I guess I'll just continue. Can you see this? Is this too dark to read? Yes? I don't know. I'll continue over here. So before going on to the approach using Kähler geometry, let me tell you where the motivation for the problem comes from and where the approach actually originates from, which is the algebro-geometric side of this story. It's mostly really a history lesson rather than anything groundbreaking. But at least the classical way of approaching these problems is to use Mumford's geometric invariant theory. So in most moduli problems, the classical approach is to form moduli spaces using this quotient theory in algebraic geometry. Mumford's GIT for geometric invariant theory. And actually, this has been extremely successful in moduli theory. It works very well, kind of miraculously well. In particular, it works perfectly for curves. And unfortunately, the example of curves is kind of misleading in that it doesn't work in higher dimensions, at least in the nicest possible way. It fails in higher dimensions. This was expected from some work of Shepard-Barron in the early 80s, but the definitive paper is by Xiaowei Wang and Chenyang Zhu. So somehow, even though GIT does everything you could possibly want for curves, in higher dimensions you have to take a different approach. On the other hand, GIT is so successful, you might think that maybe I should just modify GIT a little bit, and that's what case stability does. So case stability, I think you should think of it as the modern approach, the modern version of geometric invariant theory for polarized varieties. Case stability is, or should be seen as, the modern approach, or the modern version, say, of GIT for varieties. On the other hand, while geometric invariant theory gives you some toolbox in which you can actually create moduli spaces, case stability gives you the right moduli condition, but doesn't actually give you any construction of moduli spaces. So it's not a genuine GIT condition. And what that tells you is that there's no clear way to form moduli, so it's more of a case-by-case kind of thing. But at least it seems to recover pretty much everything that we were able to do in moduli theory, in particular those examples that I mentioned before. And mostly, well, for all of those examples, this is work of Odaka. So briefly, first of all, in the canonically polarized case, so the case where you take the canonical class to be ample and your polarization, so L is equal to Kx, this is always k-stable. And I'm really talking about smooth varieties, but actually you can even relax this a little bit. And again, in the Claviau case, you get a similar answer, which is that if X is Claviau, then actually for any ample line bundle, the pair XL is k-stable. So XL is k-stable for all L. And what this actually tells you is that these moduli spaces that I mentioned over there can be seen as moduli spaces of k-stable varieties. On the other hand, while this theorem tells you that these objects are k-stable, these polarized varieties are k-stable, it gives you no hint as to how to construct the moduli space, and then you still need to rely on these techniques. So while the moduli spaces are moduli spaces of k-stable varieties, it doesn't actually tell you how you should construct the moduli space using case stability itself. Okay, so at least it does recover the classical examples. The question then is, does it answer this refined goal? Namely, does it give you a Hausdorff moduli space? And the answer is at least it does in this Fano case, so it rules out the example I mentioned. And this is a result due to Li Wangzhu, Odaka. Sorry, Philip. Yeah, so at least in the Fano case, case stability does give you a Hausdorff moduli space. So there is a Hausdorff moduli space in the Fano case. And actually, you can even compactify the moduli space if you allow mildly singular Fano varieties. So it has a modular compactification. It has a compactification as a moduli space. So it can be compactified by including certain k-stable singular Fanos. And this is as good as you could hope for. So k-stability completely answers the refined goal. I think given these examples, you could see that k-stability should play this kind of unifying role in moduli theory. That there were lots of special cases and special constructions, but actually it's really k-stability that's the unifying theme of these constructions. Okay. On the other hand, actually, the motivation for k-stability was not related to moduli theory, at least explicitly. And this finally brings me on to the Kähler geometry aspect of the story. So this notion of k-stability, which is completely algebro-geometric, actually came from considerations to do with constant scalar curvature metrics and Kähler-Einstein metrics. So it arose precisely through Tian and then Donaldson through Kähler geometry. Although we just saw this in the last talk, let me remind you that if omega is in the first Chern class of an ample line bundle is actually a Kähler metric, then first of all, one defines the Ricci curvature of omega as the corresponding curvature of the induced metric on the canonical class or anti-canonical class. So it's I del del bar omega to the n. This is in C1 of x. And you define the scalar curvature to be the contraction of the Ricci curvature. So this is the inverse Lefschetz operator, just the usual contraction. Log, yes, thanks. Certainly. Yeah, and who knows, there might be a topological number or something, minus? Who knows? C, whatever. Okay, so then you say that a Kähler metric is a constant scalar curvature metric if the scalar curvature is constant. Is constant scalar curvature Kähler metric. As before, this is abbreviated to CSEK. If S of omega is equal to a topological constant, the average scalar curvature. So this is actually a constant. Yeah, actually, in this case, it's even a rational number. And these are, you should see these as canonical Kähler metrics. In a Kähler class, you've got loads and loads of Kähler metrics. And these should somehow be the best representative and should reflect the geometry of the polarized variety in some way. So vaguely, these are the canonical Kähler metrics. Okay. Very good. Just to write this down, although I'm sure most of you know this, in the Fano case or the canonically polarized case or the Claubiau case, this is just the Kähler-Einstein condition. So if C1 of x is either positive, negative, or 0, then CSEK is the same thing as Kähler-Einstein. Okay, and then this conjecture that was mentioned in the previous talk, or 2 talks ago, is this Yau-Tian-Donaldson conjecture. this links the existence of CSEK metrics, which is this PDE that we know is this kind of difficult fourth order, fully nonlinear PDE, with this purely algebro-geometric notion of K-stability. So originally due to Yao, refined by Tian, and then Donaldson. Also, I think Fujiki also conjectured something like this. So XL CSEK, which is to say there is a constant scalar curvature metric in C1 of L, if and only if XL is K-stable. To give you some idea of what the state of the art is, this direction is known. So this was Tian in the Kähler-Einstein-Fano situation. Donaldson, in general, proved K-semi-stability. Stoppa, then Stoppa Sekeidi improved that. And finally, the kind of definitive result is due to Biermann-Darvas-Schlu. And OK, then the other thing is that if and only if is known in the Fano case. So L is minus kx, and again, this is the Kähler-Einstein condition rather than just the constant scalar curvature condition. The direction that Kähler-Einstein implies K-stability was due to Tian and then Biermann, and the reverse is due to Chen, Knowles, and Sun. OK. So the point of this is that you should, assuming this conjecture is true, kind of view the constant scalar curvature condition as an equally valid moduli condition for polarized varieties. So there exists a CSEK metric. This should be seen as an equally valid moduli kind of condition, because it should be the same as K-stability, which I said is this kind of unifying idea in moduli theory. So this should really be the right or most appropriate moduli condition. And what I want to tell you about today is some kind of confirmation of that goal, or confirmation of that prediction. Theorem, which is joint work with Philipp Naumann, who's actually in the audience somewhere right at the back. So there exists a Hausdorff complex space which is indeed a moduli space of polarized varieties that admit a constant scalar curvature metric. So it's a moduli space of polarized varieties which admits one of these canonical Kähler metrics, a constant scalar curvature metric. So if you impose this constant scalar curvature condition, you do actually get a Hausdorff moduli space. So this does actually answer this refined goal that I mentioned. Or at least, I mean, I phrased the refined goal as a kind of vague thing, and that you're supposed to find some class of varieties that will give you a Hausdorff moduli space. I'm not claiming that this is the most, well, I'm not claiming that it's the only such choice of well-behaved class, but it certainly seems to be the most natural class. So this gives one answer to the refined goal. Yep.
You want to fix some discrete invariant?
Oh yeah, I'll just get some massive moduli space otherwise. Yeah, so typically.
For complex space, it might be okay.
Yeah. I mean, yeah, so if you don't fix, say, the dimension, you'll get some countable family. If you don't fix the Hilbert polynomial, you'll get disconnectedness as well. Typically, you should fix some polarized variety you actually care about and just consider the connected component there. So I'll point this out. So M will be very, very big and very disconnected. Unless some topological, well, unless some numerical constants are fixed. But I think really you should just fix one polarized variety that you actually really care about, and then consider the connected components that the theorem constructs. Okay, so let me give some remarks. This is not completely from nowhere, so it builds on the work of lots of people. The first thing I should note is that this uses a very similar approach to some independent work of E.G. Inoue. Who's also here somewhere, over there. So he was working on moduli of Fanos that have a Kähler-Ricci soliton. Kähler-Ricci soliton. And he'll talk about this on Thursday. The second thing is that the novelty in our construction is really for polarized varieties that have automorphisms. So if the automorphism group of the variety is actually discrete or finite, this is due to a fairly, at this stage, classical result of Fujiki-Schumacher. From 1990, and the major difference in our construction is that actually, if you have a constant scalar curvature metric and the automorphism group is discrete, then that's an open condition as you perturb the complex structure. That allows you to construct the moduli space kind of like it's an open thing, so you can usually deal with things slightly easier. For us, the major difficulty is the fact that the constant scalar curvature condition isn't actually open anymore. Well, I'll come back to that later. The third thing is that it recovers these older moduli spaces of Calabi-Yau varieties and canonically polarized varieties. So if Kx is numerically trivial, then XL admits a Kähler-Einstein metric by Yau's solution of the Calabi conjecture. So in particular, this Kähler-Einstein metric is a constant scalar curvature metric, so we recover the Calabi-Yau moduli space. And exactly the same thing is true in the canonically polarized case by Aubin and Yau. A canonically polarized variety always has a Kähler-Einstein metric, which is hence constant scalar curvature, so we recover that moduli space as well. On the other hand, I think probably what we do is pretty much identical to what's done in the literature in those cases. If you, the point there is that both of those classes of varieties have no automorphisms or finite automorphism group. And the last thing I want to point out is that actually this whole story works for non-projective Kähler manifolds. Just notationally, it's a bit more complicated, and I think people are probably more familiar with the polarized, the projective case, but everything goes through. So it works for non-projective Kähler manifolds. So in this Kähler non-projective case, what I mean by a polarization instead of an ample line bundle, I just mean a Kähler class. And maybe I should advertise, there is also a notion of case stability in this case, and you should ask Zach about that. So even in the non-projective case, there's some good reason to think that this is a good moduli notion. Okay, so once you've constructed a moduli space, you might want to know, is there anything whatsoever you can actually say about the moduli space? And that leads us on to the second result. Can you still see that? I hope so. The second result that we prove is that this complex space is actually a Kähler space. So M admits a natural choice of Kähler metric say omega WP, and the WP is supposed to signify that this is really a Weil-Petersen style metric of the form that you might have seen before in the moduli space of curves and was constructed by Fujiki and Schumacher in the case of discrete automorphism group. I'll just say slightly vaguely that this is a Weil-Petersen type Kähler metric. Moreover, this is actually in an integral class. This is in the first Chern class of the so-called CM line bundle that we show actually descends to the moduli space that we construct on the moduli space. So this is a CM line bundle type construction. No, not discrete. No. So this Kähler metric has continuous potentials, which was my promised mildly singular Kähler metric. And yeah, so again, in the case of discrete automorphism group, both of these results are due to Fujiki and Schumacher. In the Fano case, in the Kähler-Einstein case, these are due to Li Wangzhu. So we recover those results, but again, only for the locus parametrizing smooth Fano varieties. And yeah, also this is a Q-line bundle rather than a line bundle. So some tensor power is a genuine line bundle. A corollary which seems to follow from some work of Shamar and also Grauert, which is that any compact subset of M is actually projective. So the hard ingredient there is Grauert's analog of the Kadara embedding theorem for complex spaces. Okay, what time am I supposed to finish on? 10 minutes, okay. I'm not going to get into any of the details, but probably no one wants to see them anyway. Yep.
In this case of when actually dealing with polarized varieties, is there a natural compactification?
No, I'm going to write down a list of. I'm going to write this down as a question right now. That seems like the hardest question to me. So some questions that are kind of known in the field and I have no idea how to answer. First of all, the first question is M actually quasi-projective? The moduli spaces of Calabi-Yau varieties and canonically polarized varieties, and also Fano k-stable varieties, they're all known to be quasi-projective. And you can ask the same question here. That seems pretty tricky. In particular, the point is that we have a purely analytic construction, and we have no idea how to approach any of these things purely algebro-geometrically. So the second question is, can you construct this space using algebraic geometry? So can it be constructed just using the k-stability condition rather than the constant scalar curvature condition? There's again been lots of progress in that question in the Fano case. It seems to almost have a complete answer at this stage, but maybe not quite. And the last question is Daniel's question, which to me seems like the hardest of the three. So does M have a compactification, have a natural compactification, say? So in particular, as Daniel suggested, the dream would be to have a modular compactification where you add singular k-stable polarized varieties at the boundary. I suspect that such a compactification doesn't exist, but let me make the point that this question seems to be at least as hard as the Autian-Donaldson conjecture. In particular, it's a question really about compactness theory of constant scalar curvature metrics, which is really the biggest obstacle in my mind to proving YTD. So it seems at least as hard. Because basically, the variational approach would tell you nothing about this problem.
Well, my question was actually more, was even less than 1. So somehow whether you find any sort of compactification.
I don't know, if you have a topological space, there must exist a compactification of it.
Right.
So
Complex space.
As a complex space, I have no idea. That also seems really hard, and I have no idea how to approach that. I'd love to know if there was some approach that works, say, for bundles that one might be able to use here, but I really have no idea how to answer that. Okay, so I have 5 minutes, is that? So I'll give you some vague sketch of some of the ideas in the proof, and in particular, mention some of the deep results that we rely on. So some ideas in the proof. The crucial step is to rely on this Brenel-Sekeidi deformation theory of manifolds with constant scalar curvature metrics. So one starts with XL. CSEK. And to this, you can associate the Kuranishi space, which is a versal deformation space. As follows, so this is a B, so it's a complex space, the Kuranishi space. The nice thing is that it has a universal family. Actually, B naturally, most naturally maybe, lives inside H1 of X Tx, the first cohomology of the holomorphic tangent bundle. And the central fiber is isomorphic to XL. And if you have any other family, YH over S, then locally this is the pullback of this family over B. Which is to say you get a map from S or some small neighborhood of a point in S to B such that the family over S is actually the pullback family from the 1 over B. Rather than really go into the details, let me just say then that if G is equal to the automorphism group, then G actually acts on B, locally at least. And the theorem due to Till Brunel and Gabor Sekeidi, what they prove is that okay, so if you have some XP LP sitting inside this universal family, then you get an equivalence between XP and LP being CSEK, and P being GIT stable. So we have this reductive group G acting on a complex space, and then there's a natural notion of GIT stability for that problem, even in the analytic category. And you get this equivalence. So what we then do the main point really is that if you take the GIT quotient of the orbit of this B modulo G, so what we show then is that first of all you can actually take this quotient, and second of all that this is a local moduli space. So in the process here we actually use this statement that constant scalar curvature metrics are unique in their Kähler class. And we also use some ideas of Inouye in understanding the stabilizers of deformations of CSEK manifolds. And then once you have the moduli space, you want to glue these local moduli spaces together. For this, we use this also very deep result of Zhuxiang Chen, Song Sun, which tells you that CSEK degenerations are unique when they exist. And that allows us to glue the not stable orbits, the strictly semi-stable orbits together using this Kuranishi theory. That's pretty vague, but if you have more questions about it, you can ask me afterwards. So I'll finish here. Thanks.